So this lecture is on systems of particles, and we're going to be looking at systems of particles and ultimately looking at collisions and other things, but we need to do a little bit of work first on the basics. First thing we want to talk about is something called the center of mass. And in a system of particles, the center of mass is a point in the system that moves as though all the mass was concentrated at this point. When we do our calculations, we're going to deal with two basic situations. One is where we have a countable number of devices or mass particles, and we can actually compute the center of mass in one dimension or whatever. And then we deal with bodies where we have literally 10 to the 20 particles, and counting the particles is no longer practical, and how we would proceed in those directions. Before I do that, though, I'd like to mention just some examples of this and how this works. Perhaps you have seen in the past, we have a water glass like so, and you would take a spoon. So here's a spoon, so, and you take a fork, and you jam the tines on the end of the spoon, like so, and we put a toothpick here. And then this business is set on the edge of the glass, so it'll look like this. I'm not an artist, but you get the idea. And so it seems completely improbable that this assembly of the spoon and the fork together would sit off the edge of a glass. And you generally want a glass that's solid enough that it won't fall over or something like that. And the question is, of course, why might this happen? And the reality is that here's the center of mass, pretty close to it anyway. So you've got the spoon's ladle and the tines of the fork. There's more metal, more mass there than in the comparatively narrow handles. Now the handles are longer because you want your tools fairly balanced, but generally speaking, the ladle or the forks are slightly heavier than the handle is. If we put a toothpick through there that's balanced left, right, or pretty close to it, then this will come out here, and since both of them are bent this way, the center of mass moves out into a location in the middle of space. And so by putting this toothpick here, you can actually hold them on your finger too, very nicely. And it seems like it's magic, but it's pursuant to this same idea that that is the point where this would happen. Another example would be an age-old sport called the high jump. And most of us, when we were children, we did track and field of one kind or another and ended up doing this, most of the time probably looking fairly silly doing so. And there were basically three types of, three techniques I should say, maybe instead of that, we'll just say techniques. Generally speaking, when you were young, you're not permitted to cross the bar in any way where you are head first in some way or other, or sometimes even in such a way that when you finish your jump that you will land in a pile. So that's what they would have, a sand pit that would help a little bit with landings, but you certainly weren't going over the bar into a sand pit with landing on your back or something like that. That wouldn't be realistic. And so you generally learn the scissor jump. So the scissor jump, you're going to use as you get close to the bar, you'll swing the near leg hard upward. This will give you some lift. You'll jump off with your other leg, and as the raised leg goes over the bar, you quickly lift your right leg. And when that happens, the person is, let's suppose, something like this, going over the jump, and their center of mass, of your body is roughly behind your belly button. So we're looking at a center of mass here. If you look at the distance here, this person is clearing the bar with a center of mass that's actually well above the bar. It's a very inefficient jump. But of course it's a schoolyard. You won't worry about these things too much. In later times, or not so much later times, but more advanced athletics, perhaps at university or something like that, where you had landing on a crash mat, which is a mattress that's nice and thick. So when you land on it, there's a lot of compression. You learned last year from Simple Machines. That's what we call a cushion. Okay, let me get it right now. Yes, a cushion. Pillows are static, cushions are dynamic. So the cushion is what we needed there for safety purposes, and by maximizing the displacement, we reduce the forces and hopefully prevent injury. And just as an aside, if you look at old games where people were pole vaulting, and they're landing in a sand pit, it's pretty crazy compared to today. So what would happen here is something called the straddle, or some people call it the Western roll. But here the athlete was basically prostrate as they went over, with over the bar, kind of like this. So they would come up to the bar, and the bar would be ahead of me here, and they would swing like this, using their legs to go over the bar. If you get the technique, which is kind of tricky, you have your center of mass here, and it's much closer to the bar than the scissor jump is, making this a far more efficient technique. And this was the way to do it until the late 1950s. And along came New Zealander Dick Fosberry, who invented what is known as the flop, or, well, originally the Fosberry Flop. So if we look at the bar on an angle here, the athlete's going to go over the bar, kind of, this is extreme case, like so. Now, most athletes can't arch their back like this. It doesn't quite go that well. Sometimes we end up bending our abdomen or stuff. But what you'll notice here, which is pursuant to the spoon and the fork demonstration, is that depending on how fortunate you are, your center of mass can actually be below the bar. And so this makes the flop the most efficient technique. Now, when a athlete in the games today goes over the bar, they're just going over the bar. And so the technique of how aggressively you can arch yourself over the bar and all the rest of it. So high jumpers tend to be very slim, tall people, and take advantage of those techniques. Their center of mass is higher than a short person. They don't have to jump as much to cross the bar. So there's other factors there too. But it is all an interesting everyday example of how center of mass affects performance. Now we can set up our coordinate systems here to compute the center of mass between two objects. So the center of mass of two objects. Now, one of the things that you can do is to try to create your own frame of reference to your advantage, which is as easy as possible. So if we have two masses, M1 and M2, you probably want to have your axis go through one of them, saving some calculation. And there's nothing wrong with that. If we did that, we're in an interesting situation. So we want to find this balance point here, this center of mass. Now let's think about it before we get into the calculations. If we have a massive object on this end and a comparatively light object on this end of the pointer, you're going to be balancing this thing over here somewhere. And if they're even, it'll be in the middle, and if it's heavier at the left, then it'll be over here. We would fully expect that. Thankfully, it's exactly, and it's linear, what we would expect it to be. So if we look at the distance here, so you can say the displacement, we'll use x for this because it's a special kind of displacement. And then we'll say xcm is equal to m2, which is the one further out, divided by the sum of the masses times the distance to m2. So that's going to be this distance here. Well, let's just see how this works. If, and again, using Van Bemel's law of extremes here, if M2 is really big and M1 is inconsequential, well, then you'd have M2 over M2 is 1, and the center mass would be at M2. That works. If M1 was substantial and M2 was significant, then this would be basically almost 0 over a number M1, which would be 0 d2 and put us here. So the law of extremes convinces us, yeah, this looks like it makes sense to us. If we're not at the origin, and that can happen sometimes because of the geometry of where things are situated. If we're not at the origin, let's say we're here, like this, and we seek once again this mysterious balance point between these two. Now, it's very important too, everyone, as you learn these new ideas, you really have to be careful, because it is easy for us to run off and start a problem and start using definitions that we used out of our own mind of what the words, quote, mean, okay? It is critically important, and I can't stress it enough, in this subject and moving forward into more difficult materials, that you learn the definitions, whatever they are, not just the written material, which many students can recount, but they can't use it. You need to learn the standards of what the words mean and what the actual definition is of a given set of circumstances. Because the problems you're going to get are going to be multi-layered. And you might have a question 2 or 3 chapters hence that deals with something else, but ultimately has one of these things as part of the math. So you have to be very careful that you don't get fooled on these things and create some trouble for yourself. So here we have a D1, a D2, and the desired XCM. All right. So here we have the more complicated case is equal to M1 D1 plus M2 D2. I think I'm going to switch to X's here because we're using an X for this one. It probably makes more sense. So let's just do that now. And then over M1 plus M2. Now the nice part with this is that you can extend this for large systems of numbers, and we could also make it a vector situation as well. So first we could say for n greater than 2, we have xcm is equal to 1 over the capital M times the sum of mkxk over n, and m is the sum of all the masses. Okay, so this is often the case whether it's a sum or an integration. In this case, we use a capital to represent the sum of all the smaller ones. And so if you're just reading things and trying to connect the dots, that's one of the conventions that's very commonly used. Vectorially, you would have XCM equals 1 over M times the sum over N of MK XK as a vector, where M is the sum of the masses. And so this would be a vector, a position vector of each mass in whatever dimension you're dealing in, and you simply sum them as you have. So there's no real difference to that. Now, what I wanted to, I'll finish this talk here. This is a fairly short segment on the solid bodies. In advanced placement physics, I don't derive these equations for you. But let's look at the basic idea behind it. So, center of mass for solid bodies. So here we would have, so extrapolating our work to a very large number of particles, requires a different approach. So we have an uncountable number of particles, and so we have to, if we want to compute a center of mass, we have to do it a bit differently. It's based on geometry. So using calculus, we have the center of mass, XCM, is equal to 1 over M times the integral of XdM. And it's an easy equation, but of course, what does all this mean? And so, recall that density which we'll say is the Greek letter rho. So P's and rhos look very similar, especially with cursive writing. I've got a back tail on my rhos, and to distinguish them, it seems to work. And rho is going to be equal to dm dv. And this then would be extrapolate to big M over big V, and I'll put here if constant. So this leads us then to a discussion of the shape of the object more than the mass. In other words, the distribution of the mass, if you will. Then XCM is equal to 1 over V times rho, or sorry, times the integral rather of x dv. And so this gives us a chance now to look at the shapes. It's distributed as a ring, as a cylinder, you know, as a tube, as an annulus, and all the rest. So it converts the computation to one of geometry. I'd like to add, just at the end of this unit on center of mass, if we have objects that are not symmetric, this water bottle, for example, is still fairly symmetric since it's a cylinder with a cone shape on it and so on. But we could say, think of a potato or some other obtusely shaped device. Obtaining the center of mass of these devices often has to be done truly by experiment. You can calculate and estimate ahead of time, but you still have to position things with care, and you may have to test to do so. And so when we get into complex things, the physics behind it, the modeling behind it, and the guesswork behind it becomes quite involved. If you think of something like a spacecraft where we have to spin it sometimes to equalize the heat on both sides, or we're spinning it for stability purposes and so on, the positioning of everything inside the spacecraft is necessary to ensure the center of mass is where they think it is. If you are firing your rocket engine, you want the thrust to be on a line with the center of mass. And this, of course, will change because you're burning your fuel in a dynamic way. And so the thrust of the engine has to be, the cone has to vary slightly to continue to exert that thrust in that direction. You can, of course, exert it slightly to one side or the other to cause the rocket to turn, but of course, under those dynamic circumstances, you want that to be fairly slight. So it wasn't just a matter, for example, of putting equipment in a spacecraft or moon rocks and so on. It's also a matter of where, so that the center of mass is within limits, is where you expect it to be. Similar things happen with an airplane. Airplanes land and have filled with cargo and new passengers who sit in different seats. The airplane is filled with aviation fuel and so on. And so there is a center of gravity computation that is made and may well be partly measured by the landing gear itself to know that the aircraft's center of mass is within limits. What you want to make sure of course, is that when you try to maneuver the airplane, it will go where you expect it to. If it's too heavy on one side from the deck, it could easily lose control. If you're putting cargo in if it's a cargo freighter type airplane, then the cargo is strapped down very aggressively, because if fairly heavy objects were to slide and roll, even if they didn't break through the skin of the airplane, you could end up with an unbalanced airplane that would be beyond the ability of the flight controls to bring it back, and this would lead to probably an accident. So there's a lot of interesting things here when you get away from the relatively simple examples I showed you. We get into the real world, the three-dimensional world examples of computing the center of mass in the sense first of center mass calculation, as you'll see soon enough, also the moment of inertia. We'll deal with solid bodies, so no liquid spheres, no bodies that deform, okay, all of those things. And also our bodies will be homogeneous in that the density is going to be considered constant. All right, and so nature is generally not so kind. Planets and large objects are almost all differentiated. Perhaps some smaller materials for manufacture may well be uniform if they're made of the same material. It'll depend on how precise you need to measure something. And of course, when we see things like the planet Jupiter or the Sun, the rotation rates are different depending on latitude, because again, you're dealing with, in many ways, a fluid that is held together by gravity. So it becomes a very interesting computation, but of course, vastly more difficult than anything we're talking about here. Okay, so that then is an introduction to the center of mass, a few aside lines, and some basic calculations for it. Thank you for watching. Again, if you find this channel useful, please consider subscribing, tell a friend, and we will see you once again. Thank you very much.